Boom. Hello and welcome back to Calculus 1. We are starting chapter 4 on application of derivatives. This is the chapter where we learn about min-max values, optimization, that's the word problems. We learn about linearization, we learn about numerical calculations, and then we end in 4.9 with lecture on integrals, also known as antiderivatives, the way to undo the derivative. We know that we have inverse functions that would undo function calculations. So now we will have integration that will undo derivatives, which will lead us into the last chapter, chapter 5, eventually, that is all on integrals. It's only 5 sections, but it's very important to set the stage for Calc 2. So, in 4.1, we are talking about minimum and the maximum of a function, and you could have many of these. Just think of a sine wave that has infinitely many maximum values and infinitely many minimum values. Also think of functions that do not have min and max, like e to the x does not have min and max, or ln x does not have min or max. So there are certain functions that do not have min and max. Another example, 1 over x is also a good one. No min and max there. But then you do have functions that have min and max, like, x squared has a minimum, definitely, right? So, and then there are other functions that we'll see. But we are also mainly concerned with composite functions or polynomial of the higher order. There are many different functions that would have min and max. They could have one or both. It's just, a whole bunch of stuff. I like to start by considering a function that goes like this, where one peak is taller than the other. And if you remember from your from chapter 3, we used to draw the horizontal tangency on min and max because our derivative there was 0. And I know that these two are maximum values. Leave some space. This one is a minimum value. Good morning. So, sure, we can all spot min and max values very quickly. We know what they are, what they mean, right? The highest point and lowest point. But calculus is a little bit more picky than that. There are different types of min and max. If you observe the two max values presented to you, one is higher than the other. Also, if you consider the two max values, if you consider a min value, you don't see any other min values, but you see a whole bunch of points that are lower than that minimum value, right? So now, we are having a concept of min and max, but now we are separating those min and max, those minimums and minima and maxima into categories, one of which is absolute and local or relative. So if you are observing this diagram carefully, you would see that you have a local maximum because, and it's local because all of this stuff here is taller in the y value than your maximum on this side, which makes it a local maximum. It's the boss in its own backyard. Right here, That's the maximum. And we call it a local maximum, just like a mayor of a town or a governor of a state when there are United States, right? You have a governor of New Jersey who's the boss in his own backyard. Or if you want to do it on a state level, you know, you have a mayor who's the boss in his own backyard, in his own town, right? There is the absolute one, right? Now, we also have possibility to have a local min or max in this way. And that's, again, local because all of these points are lower in y value, and all of these points are lower in y value. Therefore, that makes this a local min. Do I have a situation with functions where it's absolute min? Sure. Just draw x squared function. There you go, x squared. Done. This puppy over here, right, is going to be absolute min. So sure, we can have absolute min, absolute max, local min, and local max. Can they all show up on the same graph? Yes, they can, right? If you consider damped oscillators, which is something that you actually see all the time, you have pendulum, right? So if you have a pendulum and you swing it one way and let go, it's eventually going to stop, right? Due to gravity, air resistance, and everything else that is involved. Now observe, this is the longest distance you have that it will cover, and if you consider the formula, right, for it, it will, you will learn this type of modeling for damped oscillators in differential equations, for instance. Now, the graph in time for these things would be, so you swing on one end, and it goes like this. And it stops. And this is distance. So here's your ABS max, because no other point is taller than that one. And here's your ABS min. And here's a whole bunch of relative min and max, infinitely many of them, right? Because as t goes to infinity, the object stops. So you can have a function that has absolute min, absolute max, followed by infinitely many relative or local min and max values going to infinity. Or you can, what would be the formula for this? Distance d equals some constant c e to the negative at cosine bt. This is actually formula that you will obtain when you solve differential equation, and then obviously something like this would be used in physics in a lab to show that this formula actually does govern physical reality, and you can measure these things in in the lab. There is this professor of physics at MIT, Professor Lewis, who actually takes, I think, 2-3 pound steel ball that is suspended at the ceiling. He puts it next to his chin and then lets go. The ball goes all the way across the room and then comes back for a fraction of the inch. If the physics was wrong, he would be dead, because a 5-pound ball going at that velocity would definitely crush his skull, like nothing, you know, like hitting a stick of butter. But we know in physics that the ball is going to lose some energy due to air resistance, gravity, and so on. So technically, he releases it when it's touching his chin here, and the next time it comes back, this missing distance is the one that keeps him alive. That's the thing. You can actually watch this video on YouTube. He does all of these experiments in class, actually. So this is the story of min and max. Very simple, right? You understand already the concept that you do have min and max of a function. You also now understand that there are different kinds of min and max values, absolute, or global one, and then relative and the local, right? Or local, whatever words you want to use for that. You just have to make sure that you know, right, that local min happens when you either have when you have any type of a smaller value. In this case here, for x squared, this is absolute min because there are no lower values than that vertex ever. And now, before we start calculations, if you have a sine function that will do this forever, each one of these peaks is the absolute max, and each one of the bottoms is the absolute min, and we have infinitely many of those, right? So they're all ABS. There are no higher points, so ABS max for each one of these, and then ABS min for each one of these. Cool? The goal of this section is not only to teach us about what exists out there, but also how to compute them, because we are always considering application problems. We are going to have in 4.4 word problems to optimize. We are going to look for maximum volume, minimum surface area. We're going to look for the minimum cost, maximum profit, and all of these things that will be computed there. So we want to actually figure out the algebraic way to find these locations where extreme points happen. Before we do that, I'm going to write a sentence here in red, which states that min and max occur at critical points. And now we need the definition for the critical point. So min and max occur at critical points. I am going to box that statement. Is this all that occurs at critical points? No. No. There's more than that. Right now we're only focusing on min and max. At critical points you also have asymptotes. At critical points you also have something called inflection point. Critical point in Calc 3 will also include a saddle point. So min and max is not nearly the end of the story for critical point. Critical point is going to have a lot of roles as you push through calculus layers. But for right now, we want to say that min and max occur at critical points. So if you find critical points, chances are that that critical point will be min or a max. So not guaranteed, but the chances are it will be min or a max. So definition of a critical point. A point of f of x is called, or a point in the domain of f of x is called a critical point if, number one, the first derivative at that point is equal to 0, Or, number 2, the first derivative at that point does not exist. That's it. What function better to use than our good old friend x squared, right? Way to find the cheapest possible function, right? So whether you write y equals x squared or f of x equal x squared, right, either way, we are going to consider x squared. So what do I have? Want to find critical point. So what do? Well, I take the derivative, which is 2x, and I set this equal to 0. See, I am forcing that horizontal tangency. So here in blood, we set equal to 0 because we want to force horizontal tangency. Forcing horizontal tangency. Well, what do I have here? I have a very simple algebraic equation to solve. I have 2x equals 0 from where x is equal to 0. The x-coordinate of a critical point is called a critical number. Critical points have x comma y. So now I will calculate the y value as f of 0 is equal to 0 squared, which is 0. So now I have 0, 0, and that is the critical point. So we would take the function, we would find the derivative for the function, and we set that derivative equal to 0 to find the x values at which we have derivative 0. Why are we looking for 0 derivative? 0 derivative gives us the horizontal tangency. When your function has horizontal tangency, you have min and max show up. And that was the picture that I drew, the first picture that I drew there. You have any min, any max always has the horizontal tangent line going through that min and max. Horizontal tangent line, well, horizontal line has a slope of 0. So we are forcing slope to be equal to 0 and looking for x values when that occurs. Anytime when the slope is 0 for the tangent line, you would have min and max. So now I found critical point 0, 0, and because we know what the x squared looks like, right, which is the opens up, so this particular point here is the maximum point. It's a max point. We also min point. I said the min, please pay attention. It's a min point. We also know it's the absolute min. We also know that. Well, let's just call it a min. What you see here is the full problem. Can I make this hard? No. Can I make it annoying? Sure. Toss in 3 ln's with a sine and a inverse cotangent, and there you got it, right? That's just making it annoying. But the concept, I really can't make hard. Because all you need to do is to take derivatives set it equal to 0. It becomes tricky here and there. What if when it doesn't exist, right? So if I have f of x equals to absolute value of x. Well, absolute value of x So absolute value of x is defined as x and negative x. Have the signs opposite. Now, we can't take the derivative of absolute x, but we can take the derivative of the definition of absolute x. You just take the derivative of each line independently. So, f prime of x would be the derivative of x, which is 1 for all x's larger than 0, and negative 1 for all x's smaller than 0. Do you see that we have a problem at 0? At 0, the derivative is trying to be both of these values, and it can't. Here's the graph for the derivative. So this is your y prime. We have 1, and we have a negative 1. So this concludes derivative at x equals 0 does not exist. Which was our rule number 2. So, see, remember? So either you are setting it equal to 0, or when you find the derivative, you see that the derivative does not exist at a certain point. So our rule number 2 here says derivative at x equals 0 does not exist. So x equals 0 is a critical number. Leading us into 0, 0 critical point, and then that leads into a minimum to solve the problem. We know it's absolute minimum, but don't care about it right now. We'll deal with it later. This is the thought process that you need to go through. So you know you have to take the first derivative, and then when you take the first derivative, you see what you have and what you're working with. Another example, our friend 1 over x. F of x equals 1 over x. Well, immediately f prime of x is equal to negative 1 over x squared. So that's the derivative. And when you set this equal to 0, and then cross multiply, what do you get? You get negative 1 does not equal 0, right? Because the x squared, when you cross multiply, x squared will multiply into 0 and die, right? Now, statement like this means no critical points. No critical points means no min-max. And that's okay. I already said that certain functions are not going to have min and max, and I listed 3 of them. So here's the 1 over x, which is one of the 3 which I listed. So this particular function does not have min or max value. Both of these lines, one that goes up and one that goes down, are going to infinity. They never stop, and because they never stop, going to infinity, going up to infinity, they never get to reach the maximum value to settle at that maximum value, so that becomes a maximum. Does it make sense?
So are all discontinuous functions like that?
No. I can make anything into a discontinuous function. right? We can have a discontinuous function that it's a piecewise function with a piece coming in as this, and which is the absolute x, right? And then, I mean, just negative x, and then have x squared minus 2 go up. Clearly has an absolute minimum at the black dot at negative 2. It's a discontinuous function with a jump from 0 to negative 2. It's also a piecewise function to add to that, right? So the only thing is that you have to work with what you have. And if you are able to graph it, that's perfect. You're in luck that your calculators will work in Calculus 1, right? I mean, you can't use it on the test, but your graphing calculator would work. So you can use the graphing utility to see, because we always deal with functions in Calculus 1, unless it's implicit differentiation. You don't have to graph it. Calc 3, this concept becomes a little bit trickier because it's 3D surfaces, and your TI 83, 84 are useless. They don't graph 3D surfaces. And then you have the min, max, and a saddle point. And that's even more calculations and things to consider. So let's take a look at one more of these. F of x equals e to the 2x. Can you work this one out on your own? So what's happening here with min and max?
Is it 2?
Is it? Did you calculate that, or you're making an educated guess?
I mean, that's what I calculated, but maybe I'm wrong.
You mean x at x equals to 2?
Yeah.
Let's see what else is there.
We'll have to revisit this box.
Oh wait, Halloween is on Wednesday. I'm not gonna see you. Oh, I'm coming. It's all black with your white. I tested it on Thursday in class. It was interesting. Students will very authentic everything. So let's take a look. What is the derivative of e to the 2x? 2e to the 2x. We set that equal to 0, and there's no solution. So, no solution, no critical points, no min max, and we move along. Textbook problem 35 for you to enjoy. Says f of x is equal to 1 over x plus ln x. It's problem 35. you're supposed to take the derivative, set it equal to 0, solve the equation. let's take a look at this one together. And then we have one more thing to cover, and that's it for this lecture. So we always take the derivative, so we can set it equal to 0. We have negative 1 over x squared plus 1 over x, and then we set this, I'll put it in red, we set this equal to 0. So now we can ship negative term to the right side. So we have 1 over x squared, from where we cross multiply, and we have x squared equals x. Now we move x to the left, we factor x, and we have two answers here. X equals 0 and x equals 1. So now we have to drop x equals 0 because there is a vertical asymptote at x equals 0. So you cannot have a min or a max point at the vertical asymptote, right? The function doesn't cross vertical asymptote, so it cannot have min or max value on vertical asymptote. So we have to drop that. So the only critical point we have is, this critical number is at 1. You can go and calculate critical point. Let me put this as a critical number. So critical number, Cn. And now we go and find f of 1, which would give us the value. And that is going to be 1 over 1 plus ln of 1, which is 1. ln of 1 is 0, 1 over 1 is 1, so 1 plus 0 is 1. So 1, 1 is the critical point. Now, do I know if this is a min or a max? Well, right now, I don't, right? I'm not familiar with the function. I'm not sure what this looks like. So the only thing that I can do for now, before we cover 4.3, is to test a close by value. So test x equals 1.1, let's say. So we go f of 1.1 is 1 over 1.1 plus ln of 1.1. Now, why are we testing this? We are testing this because it's going to give us a y value that will be bigger or smaller than 1 that we have in a critical point. So I'm going to jump into calculator here. 1 divided by 1.1 plus ln of 1.1, and the value is 1.0044. So 1, 1 is what? A min or a max? What do you think? Because you have the value.
It's got to be minimum, right? That number's larger.
This number is larger, so it's a minimum. Yes. It's a minimum. Observe. For a minimum value, in order for this to be 1, 1 minimum value, slightly to the right at 1.1, we have 1.0044, which is taller in y than our original y that we were looking at. Do we all agree on that? That a value at 1.1 is taller? Does that make sense? Which makes this one a minimum. So that's the thought process of how you get it to be a minimum.
Is that 1.1 is min or 1?
No, 1.1 is a minimum.
1.1.
Yes. And this we used as a test point. Now we're not going to use this because you guys are going to see 4.3 today, so the whole thing is completely not necessarily good morning. Now, the last part of this lecture is called absolute, min, and max. So if I put a linear line like this that goes on forever in both directions, does it have min or a max? The answer is no. It does not. It does not have min and max because it will forever go up, forever go down to infinities, and no min or max. But now, if I take the same line and I just chop a piece of it, does that have min or max? And the answer is yes. In this case, the endpoints. So here is your ABS min, and here is your ABS max. So what is the difference between the two? If I am to give you an equation of this line, it would be the same for both. Call this, I don't know, 1/8 x plus 1. It's you know, whatever. See, the trick is that this one over here has domain is chopped off, right? We call it a restricted domain. So this part of the line here lives on AB, where this line over here lives on negative infinity to positive infinity.
So anything with an infinite domain is not going to have an absolute minimum or maximum?
Oh, it can. Absolute, well, x. There's your absolute min. Or
Okay.
this way, there's your absolute max, right? It can. The beauty is that anytime when you chop it off, you guarantee it to have one. Okay? So, on the left picture, we have no min or max on infinite domain. So if the domain is infinite, you could have absolute min or max, or you don't have to have it. But when you restrict the domain, you must have absolute min or max. So, in red, so over here I'm going to say any function on closed interval AB will have ABS max and ABS min. And now you have problems in your textbook 43 through 68. That's more than double of what the initial exercises are. To practice this. they throw at you regular polynomials, exponential, trigonometric, more trigonometric, cube roots, like all kinds of stuff. Inverse trig with a cosine and negative inverse. This is a product rule I see in 56. So it's a quotient rule in number 50. They toss a lot of stuff at you in this section. This is the best section to practice, obviously. Problems 43 to 68. On the other side, you have the secant, more polynomials, more e to the x, e to the negative x. There's ln x over 5. It's a lot of cool stuff. Let's do 2 of these. How about 49 with a cosine squared? I know how much you love trig. So, and we barely did any. So f of x is equal to cosine squared x on interval 0 to pi. Alright, so I have a closed interval. That means this is guaranteed to have ups, min, x. Now what I'm going to do is I'm going to rewrite my function cosine x as cosine inside the square, like this. So now when I take the derivative, it becomes 2 cosine x sine x as a chain. Derivative of the inside, inside the cosine. So derivative of cosine is, negative sign, sorry, so it's negative. So it's negative. And if you learned any of your trig formulas, you know that this is now negative sine 2x. I'll write the formula down if you don't remember. It says sine x is equal to 2 sine x cosine x. And that's exactly what I have, other than that minus that it's floating around. So now I have negative sine 2x is equal to 0. So that's as good as sine 2x is equal to 0. And if you draw, now you have to solve the trigonometric equation. If you draw sine, you know that the intercepts over here, because you're looking for zeros, are happening every pi. So they are happening every pi. So what do I have? I have sine I have 2x equals to pi. Well, I have equal to 0 plus n pi, meaning every pi there is this. So what is my x? My x is n pi over 2. N being 1, 2, 3, 4, going on forever. It's just counting. Does this make sense? Well, hell yes. Because do we all see that the sign is going to have zeros at 0, pi, 2 pi, 3 pi, right? So this is capturing every next pi unit. And now you need the x alone, so you have to divide by 2 both sides. And don't worry about the 0 part, obviously, so you get n pi over 2. Now, because we are on 0 to pi, we will calculate the endpoints. So we have f of 0. F of 0 is going to be cosine of 0, everything squared. Cosine of 0 is 1, 1 squared is 1. And then we have f of pi, which is cosine of pi, everything squared. Cosine of pi is negative 1. squared, it's also 1. So it appears that these endpoints are both value 1. And now I have the point inside. But I only get to use n equals 1 because n equals 1 will give me that x is pi over 2. And that is between 0 and pi. Remember, we have the interval 0 to pi. Now, if I am to use n equals to 2, n equals to 2 would give me pi, but I already have that. N equals to 3 pi over 2, and 3 pi over 2 is not between 0 and pi. So this is what I have. And I calculate f of pi over 2, which is cosine of pi over 2 everything squared, which is 0 squared, which is 0. And what do I have? I have 0, 1 as a point from the first calculation, pi 1 from the second, and then pi over 2 and 0 from the third. ABS max, ABS min. And here is Desmos graph of x squared. Observe that pi is right here, which is this peak right there. So I hope you see ABS max at these two locations. The rest of the graph does not exist because we have to cut off from 0 to pi, right? That's our interval. Do we all see also absolute min at pi over 2 as we calculated? Hopefully we do, right? As you are learning this section and the rest of chapter 4, especially when graphs are involved, just put the graph there, right? I'm going to now also graph the previous problem, 1 over x plus ln x. 1 over x plus ln x. No, that's not the way we want this. 1 over x plus ln x. Do we all see a minimum at 1, 1? Mm-hmm. Well, when I remove the extra garbage. This is a value 2. This is 1. This is 1, and exactly 1, 1 was the minimum, and we calculated. We had no clue what the graph looks like. We knew there was a vertical asymptote at 0. You can see this line following that, right? And we know that the vertical asymptote is there because both of these functions have a vertical asymptote at 0, right? 1 over x has it, and ln x has it at 0. This is very powerful stuff. You can calculate min and max values without knowing what the function looks like, just doing algebra. So you take your first derivative, you set that derivative equal to 0, and you get the value when you solve equation. Solving equations, well, that's your pre-calc 1, right? You're either solving algebraic equations that could be exponential, trigonometric, polynomials, right? It's going to be something, and at some point in your prerequisites for Calc 1, you covered how to solve those equations. So we have pretty much all of the variety. We had the polynomial with x squared, the rational function of 1 over x. We also had the e to the x. We had ln x. We had trigonometric function. So I covered pretty much, most of the types of functions. We also talked about absolute value of x. I'm going to leave a square root of x as a challenge to you. Please put down in your notes f of x equals square root of x minus 2. And practice that. If you have any questions, bring.
I'm sorry, what was that square root of
X minus 2.
Not
Sure.
under the...
Everything under the root.
Everything.
X minus 2 is under the radical. So take a look at min and max for that particular graph. And now we can talk about it next class. That's it for this lecture. Bye.